High-resolution image synthesis with latent diffusion models, published in 2022 by Rombach and colleagues, introduced a scalable and efficient framework for generative modeling, enabling high-quality image synthesis under reduced computational constraints. While diffusion models have achieved state-of-the-art performance in image generation, they typically operate in pixel space, making both training and inference computationally expensive. Latent diffusion models, or LDMS, address this by decoupling compression from generation. An autoencoder first maps input images to a spatial latent space, reducing dimensionality while preserving semantic content. The diffusion process is then applied within this latent space, significantly lowering computational costs. The architecture consists of three core components: an encoder that compresses the image, a diffusion model that performs denoising in the latent space, and a decoder that reconstructs the image. The diffusion model itself is a time-conditioned UNet, which benefits from the spatial structure preserved in the latent representation. A key distinction from earlier latent generative models is the choice of downsampling. Rather than aggressive compression, LDMs typically use moderate factors, such as 4 or 8, which strike a balance between computational efficiency and high-fidelity reconstruction. The model is also highly flexible in how it incorporates conditioning. By integrating cross-attention layers into the UNet, LDMs support conditioning on a variety of inputs, such as text prompts, semantic maps, or spatial layouts, without the need to retrain the generative core. This flexibility extends to a range of downstream tasks. For instance, LDMs demonstrate strong performance in inpainting, accurately removing and reconstructing missing regions of images using context-aware sampling. They also generalize well to layout-to-image synthesis, producing high-resolution outputs conditioned on spatial or semantic structure. This is particularly valuable for controllable image generation. Empirically, LDMS achieve competitive or state-of-the-art results on multiple datasets, including Celeb AHQ, FFHQ, and LSUN, across tasks like unconditional generation, super-resolution, and text-to-image synthesis. Compared to pixel-based models like ADM or GAN-based alternatives, LDMs require fewer parameters, train more efficiently, and still maintain high image quality. They scale to larger resolutions with significantly reduced training time. Latent diffusion models offer a modular, extensible approach to generative modeling. By compressing perceptual information before generation and leveraging efficient conditioning mechanisms, LDMs make high-resolution synthesis more accessible under real-world compute constraints. Follow at daily.ml.papers for more quick insights on groundbreaking research in AI and machine learning.